All right, I haven't done 60 Minutes in a couple months, and I think for those of you who were here the last time I did it, I had lots of stories about galaxies and about star formation, and so I thought for this month I'd take a completely different tack, and all my stories have to do with discoveries of planets outside of our solar system, so-called extrasolar planets or exoplanets. And so, we also came up on recently the 1-year anniversary of a NASA satellite that's devoted to discovering new planets. So it just felt like it's a good time to do this particular topic. So let's go ahead and get started. And I'm going to first talk about one of two techniques that have allowed astronomers to now discover over 4,000 planets outside of our solar system. So that's an amazing number because we effectively know about 500 times more planets outside of our solar system than planets inside of our solar system. So that's a really remarkable number, and we're learning more and more about them every day. And as technology improves, as you'll see in my very last story, we'll hopefully be finding out some really exciting things in the distant, not too far future. So one of the techniques that's used to discover planets is actually the very first one that was successful, starting in 1995, is the so-called radial velocity method. And basically this is something that occurs if you have a large planet that's orbiting a star, and it causes the star to wobble around the two's common center of gravity. So because the planet, and let me just redo this animation. So both star and planet orbit this common center of gravity, and the larger the planet, the greater that center of gravity shifts from the center of the star. And so even though the planet and the star are so far away that you really can't see more than a pinpoint of light, by looking at the spectra of these stars, spreading out the light, you can actually see red and blue shifting of light from the star as the star wobbles back and forth, moving towards us and away from us due to the motion or the gravity of the planet. And this is another animation showing that same effect. And what we're seeing here is this is a plot of the radial velocity. So this is the speed of that star that's wobbling back and forth as a result of that planet. And you can see that it gives you this sort of sinusoidal motion if the planet and the star are exactly aligned with your line of sight, meaning the plane of the planet and the star are basically level with each other. And the very first planet discovery using this method was a star called 51 Pegasi, and this was announced in 1995. So basically, over 20 years ago, almost 25 years ago. And here they've collapsed all the radial velocity data into one curve, and you can see how nicely those radial velocity points, the velocity of the star, that reflex motion as a result of the gravity of the planet, fits onto the sine curve. And this is a pretty large motion in this case. We're up to about 50 meters per second. But the telescopes and the instrumentation have improved to the point where we can now detect motions down to meters per second. So in this case, because the early instruments could only see motions up to tens of meters per second, they were discovering these really massive planets, planets that gave a bigger jog to the parent stars. And so these super Jupiters, these planets that are orbiting really close in, and so they were causing orbital periods, or they were seeing orbital periods of these planets of the order of multiple days, as opposed to years in our solar system. And so what's really interesting is that just this past month, there was a paper that was accepted into a journal that talked about this particular planet or this particular star that has a really weird radial velocity curve. So instead of that nice sinusoidal curve that we saw earlier, this is what it looks like. And these different colored points all represent different observatories. So astronomers are basically observing with multiple observatories so that they can get as much data as possible. So if that one observatory gets clouded out, or one observatory is busy observing other things, you can get data from other observatories. But instead of a nice sinusoidal, you have this weird pattern where the star has this jump in its motion and then decays back down again. And so all these points are the actual observations, and this blue line is the model fit. So they were actually able to come up with an orbit of a planet that actually fit the data. And what they came up with for the star, HR 5183, is actually, I don't think we can see the planet, a planet that has an extremely inclined orbit that's also very eccentric, meaning it's stretched out into a long ellipse as opposed to more of a circular orbit. And so here is that planet. And what the animators have done is they've overlaid the orbit of this planet into where our solar system would be. And so basically, this planet orbits in, and it gets as close as Jupiter's orbit, and then it gets much further out to about where Neptune's orbit is. And what they're able to determine is that this planet is about 3 times the mass of Jupiter and has an orbital period of about 74 years. And you can see that the error bars are quite large, 74 plus 43 or minus 22 years. This is about as good as they can get. But even though they haven't been observing this particular star for that long, because of the peculiarities of the shape of that radial velocity curve, this is, they were able to very comfortably predict that this particular type of orbit fit that radial velocity curve extremely well. And so even though they didn't observe the star for more than 74 years, they're pretty confident that this particular planet in that particular type of orbit caused that particular wobble.